Okay, so let's start with some logistics. So I just upload what I mean by doing a project. Like this is an example of a project, which is like what you need to do for doing project is first to write a report, and it's supposed to basically has like some problem statement of the result that you are interested in, and the main result, and algorithm description, and correctness proof, and complexity analysis. And this whole thing shouldn't be longer than 5 pages. So let me kind of go through this very quickly, how it looked like. So what I'm looking for is like there will be the list of projects that you can choose from some spreadsheet, and I will specify like what kind of theorem I hope you to understand. Like there will be one main result, one theorem. Like for example, this is one theorem. So you should state that in your write-up. Before stating this, to make this making sense at all, you might need to set up like what it means for everything, like what this thing means. So there's like some problem statement, and you can set up all the definition you need in one short section, and then just state what is the result, and then there should be like some algorithm that proves this result. Just describe the algorithm without any analysis, and then you prove the correctness of the algorithm and analyze its running time. So this is my example. It's like it's a short one. It takes only 2 pages. I suspect that like from the list of projects that I offer in the spreadsheet, it shouldn't take too long. Like hopefully it's not longer than 5 pages. So I encourage you to try to do this within 5 pages. If you really cannot do it, then 7 pages maybe is okay. But yeah. For the list of projects, you can look in the syllabus here, which is here. But the list is not really finalized yet. I'm still like trying to look for like a nice topics that is simple enough for you to just read on your own, and prove it in a short write-up. But like maybe within next week I should finalize this, and you can start looking into it. But for now you can also just like skim through it and see which one you like already. But just keep in mind that I might still change something. Yeah. But within next week it should be done. So for the project, you write this up like 5 pages, and then like near the end of the semester, we're gonna meet and talk for like 15 minutes, and I check that you really understand the stuff. Yeah. Okay. So that's about the project. And now, so back to what we left off last time. Just to recall, like what we want to look at is the problem of polynomial multiplication, right? You're given the list of like you're given two polynomial a and b, where they are represented as the coefficients, and you want to multiply them. That's the problem, polynomial multiplication. And so we have seen a bunch of algorithms, but then at the end we kind of look into this strategy, right? That is, instead of working with coefficient representation, we just plan to map this coefficient representation to point value representation of A and B. Once we have this one, the point value representation of A and B, then you can get the multiplication really easily. Just multiply pointwise, and then you try to turn it back to coefficient representation of C. So the key question is then, what is the point set that you plan to evaluate from this one to this one? how to do that fast. So that's the key question. And so we have seen one kind of nice nice observation that, okay, if the point set is such that it's like a negation of each other, like if you want to evaluate 2 points, x and minus x, then like you can reuse information nicely so that you don't need to like recurse too many times. Like if you want to evaluate like on 2 points, just need to recurse on 2 points in the small like on the smaller polynomial. Okay, so that's a nice one. Like you don't need to evaluate on 4 points, but just 2 points when in the recursion. Okay, so because of this insight, we think that okay, let's design our point set S to be like n over 2 pair of points that are like a negation of each other. And once we do this, we see that when we wanna recurse, well, we just need to like recurse on like each of these. When you kind of square them, they map to the same number, so it's kind of nice. Okay. Okay. So we like I hope you kind of I'm just trying to recall what happened last time, right? So it seems like if we want to evaluate A at n points like this, then all you need to do is just to evaluate like evaluate two polynomial of degree half n, like n over 2 at n over 2 points. So that seems great and nice, and like the additional time you need to spend is just order of n. So superficially, the recursion looks like this, which we all know that it goes to n log n. But can someone tell me like what was the issue again from last time? Yeah.
We would have to square each point, but that would make the positives equal to the negatives, so they would want to be distinct points.
Exactly. Like our like a strategy is to square each point when you go to recursion. If they are negation of each other, they will go to the same point if they are negation of each other. But in the recursion, like in the recursion here, the point set that we want to evaluate, they are all positive. There's no negation of each. Like you cannot pair them up, so you cannot continue this idea. So let's try like so what we wanted to obtain is something that okay, you want to get a point set that you start with like a bunch of negation pairs, and when you square them, you still get something that like there still exists a bunch of negation pairs when after squaring. And kind of to do this, it turns out that when you use like a root of unity which is a complex numbers, they are exactly what we want. Okay, so let me recall the concept of root of unity. Okay, so the n roots of unity are just solution of x to the n equals 1 in complex numbers. Okay, and so I hope that if you don't know this from last time, I hope you look up a bit. But here is the list of properties that we will need in this class. And if this doesn't make sense, look up. But I'm just gonna assume this. Okay. So basically, how many solutions are there for x to the n equals 1? There will be exactly n many solutions, which is start with 1, like 1 to the n is 1, but then another one is like this thing, like omega n, which is something in the complex plane. Which is, for example, it looks like this. Okay. Like it's just another guy in the complex plane. And then like just this thing square, this thing cube, and so on. So it just looks like this one. This is like the 8th root of unity, so there are 8 of them. Okay. And another thing that I need is that like if you look at the root of unity, like the nth root of unity, powered by n over 2, then this is going to be exactly -1. For example, this is like a omega 8 to the 1, and then do it 4 times. Omega 8 to the 4 is exactly -1. The same for this one, like omega 4 to the 2, like omega 4 square is just this one, -1. Okay? And this means what? It means that this thing, omega n to the n over 2 plus k, is just exactly -1 times this thing. So you can see that like you get like a kind of negation pair of each other here, right? And these guys are negation pairs of each other. Okay, so this is like looks like what we want. We want like a point set that looks like a negation pair of each other even after squaring. Okay, last one is that omega n to the k square. Maybe I should write it like this. Omega n to the k square is just exactly omega of n over 2 to the k. Okay. And you can verify like just you can see this example. For example, like omega 8 square is just omega 4 to the 1, for example, and this omega 8 to the 6 is omega 4 to the 3. So like at least this example like kind of verify this properties that we want, but look up if it doesn't make sense. Okay, so this is like a kind of the structure of root of unity. You have like a bunch of point set. When you square them, there are 8 of them. When you square them, you get 4 points. In before squaring, you have like a negation, like a 4 pair of negation. After squaring, you still get like a pair of negation of each other. Exactly what we want, you see. So now with this in mind, just use it. Let's just use it. So let's verify this again. Like if I use my point set Sn to be this set of root of unity, right? You can verify like algebraically that, okay, if I list this thing, all of this thing, right? I just kind of write down here in the list. Then I can rewrite it so that it looks like this guy is like this guy is just negation of this guy. No, actually, this guy is negation of this guy. So this is like this one is minus of this. Next, this guy is negation of this guy. So like the last n over 2 elements here can just write down as negation of each other here. Okay, so it means that once you square all of this, once you square all of them here, if I square each of the element here, right, then this will go to the same number. This will go to the same number here. This will go to the same number. Okay. And this is exactly the root of unity, but it's n over 2 root of unity. Okay. So I hope you are with me here. And now, so just to conclude, like the nth root of unity is exactly the point set that after squaring, you get Sn over 2. So it's the same structure but half size. Same structure that have this pair of negation. And with this in mind, you can just like do the like just follow the same recursive algorithm that we try to do. Just try to do the same like before, right? That is like try to evaluate this guy that are negation of each other, and evaluate at a square of A even and A odd. Okay. But the point set that we need to evaluate at A even and A odd is just going to be exactly N over 2 root of unity. Okay. Now we can ask ourselves, can we recurse, like can we continue like our recursive strategy on A even and A odd? And the answer is yes, right? Because this N over 2 root of unity has the same good structure that we want as as N root of unity. They still have like these negation pairs of each other. Okay. So that's it. Like with this, we basically can conclude that to evaluate A of degree n at the n root of unity, what we can do is just evaluate two polynomial, which is A even and A odd, which has degree n over 2 at the n over 2 root of unity, and spend on additional operation. So this is now the valid divide and conquer algorithm, which gives us this kind of recursion, this kind of recurrence, which is a log n. Okay. So yeah. So we are now done for one step here. We now have designed the point set such that we can evaluate n point on the polynomial in just a log n operations. Question up to this point?
Can you just go back up to the S of n over 2?
Yeah.
For 1 second. Can you show which ones are pairs of negations in that?
This one?
Yeah.
Okay. So it's going to be like the second half of this guy is going to be like, so like when you write it down like this, then this guy to the n over 4 this guy, they are negation of each other. So similar to here, like the second half, they're just a kind of negation of each other, and here is the same. The same thing happened. You can kind of look at this picture too, like after squaring this 8 point, you get these 4 points, and the second half of the point, they are negation of this first half. More questions?
Why you can use omega to substitute?
Say it again.
Yx can be substituted by omega.
Yx can be substituted by omega. So the whole point of this is that we want to evaluate A at many points. So what it means here is just what we want to do is just to substitute x by many points and get the
many points, but you only use omega to substitute.
Yeah.
But what if it's for values outside of omega?
What if so you might you are allowed to use other points, but like we design this our choice to design which point we want. And we choose omega, like omega n to the many powers, because we choose that because it allows us to get a good recursive algorithm.
Okay.
Is that answering what you asked?
I think omega is too special.
It's special, it's special, and we choose it because we can see that once we choose it this way, you get a good a recursive algorithm. It's not as you saw before. If we just choose some point set, it's not clear how to get a recursion to work. More questions?
So on a higher level, this first step, are we generating with like the down arrow, we're generating endpoints, or are we evaluating A and B?
We just choose, what we are doing is that we choose omega n, we choose this as our point set,
Okay.
right? And then we just, for each of these points, we evaluate A at every point here,
Okay.
and do the same for B.
Okay. So like the x values of those points are the omega
Yeah.
values.
Yeah. Right. So we do this evaluation of A and B, and get the evaluation point of A and B here. And now you see that to get to this point is just easy. Just multiply pointwise.
Okay.
Okay. Yeah.
So when we're actually implementing the algorithm, how large of a point set should we choose if the degree of the polynomials is not 2 to the power of something? Because when we're recursing, we need to divide it by 2 at every step.
Yeah.
So what if the degree of the polynomials is 9, for instance?
Then let's say round it to 16.
Okay.
And then work with 16.
Okay.
Yeah. That just kind of double the size of the input, but it's not big deal. Yeah. Okay. So we are done with this first step. The second step is easy. What about the third step? Okay. It's going to be the case that it's almost the same algorithm as this one. And let's see why. Okay. By the way, this step here is called what people call fast Fourier transform. Okay. I put the pseudocode in the case that you kind of want to understand everything in more details, but I will skip in class. Okay. But the idea is you have polynomial represented with coefficient, and now you just kind of need to recurse 2 times and do the same thing that we did, and just return the evaluation points. Okay. Anyway, so our goal now is to do the last step here. Okay. And how do we do this? We will do this by understand our algorithm in a different view first, and once we do that, it's going to be clear how to do the last step. Okay. So so recall that how A evaluated at this thing looks like. It's just the sum here. Okay. So it means that what we can do is that we can write down this equation. Oh, okay, good. So I claim that if I can, for example, define the vector A here to be the coefficient vector of polynomial A. Okay. This is just a vector here. And I've defined vector YA to be this guy. Just the evaluation points of A at omega to the I for all I here. And I claim that I can, this vector is related to this one by some matrix multiplication. So let's verify this, at least at this, maybe at this point. So let's see how this thing looks like, right? This thing you can write it down as the sum of a I omega n to the I. So you can see that this is exactly this vector multiplied with this vector, right? And so the next row is the same too. Like if you want to, what is this thing? It's just, this guy is just a sum of ai omega n squared to the I, which is just this vector multiplied with this vector, like a dot product between the two. So I hope you can now see that, okay, this pattern continue. So it means that like once you multiply A to this matrix H, then you indeed get this vector YA. Okay. Yeah. Just need to see that like it's just from the definition of things. Okay. So in other words, what do we get? We get that what fast Fourier transform is just an algorithm that allows us to compute this multiplication fast. Like given the vector A, the coefficient of a polynomial, you can multiply it to this matrix H, and then you get YA very fast in just n log n. Normally when you multiply a vector to a matrix, it takes n squared time. That's a trivial algorithm. But what we just learned is that for a spatial matrix H, you can do this in n log n time. Okay. So with this view in mind, I can also define like a vector B and C and YB and YC in a similar way, right? And now, so we can see that the strategy that we want to do, the three-step strategy that we want to do, can be written in this way. The first step here is just to, we are given A and B as our input, and we multiply A to H and B to H and get vector YA and YB. That's the first step that we just did. Okay. And we can do this in n log n time. And the pointwise multiplication here, what is this? It's just to multiply these two vectors YA and YB pointwise. Right? You have two vectors, you just multiply them pointwise. You get YC. This is exactly the evaluation points of C at the omega. Okay. So now what we want, the last step then, you can just say that the last step is to find a vector C such that when you multiply C to H, you get YC. Okay. So in other words, right now we have YC. You want to find C such that when you multiply by H, you get YC. So what we want is like you want to compute this thing. You want to compute H inverse times YC. Okay. And so H is a matrix, and you just ask what is the H inverse. Just to recall, like H inverse is just a matrix such that H times H inverse is exactly the identity matrix, right? So you just need to ask yourself, how does H inverse look like? And once you know how it looks like, can you multiply YC to it fast? If we can do this, then we are done. Question? All right. So it turns out that H inverse is actually very simple. Like it's just almost the same as H, turns out. So you can see, I claim that H inverse look like this. Basically, it's like H exactly, except that you replace omega n by omega n inverse, omega n to the minus 1. Right? Just replace this omega n by omega n to the minus 1 in every place, and then at the end scale it down by 1 over n. And we can actually verify that when you look at this matrix, when you multiply H with H inverse here, you get exactly a matrix, the identity matrix. I kind of short of time and I need to, but I encourage you to verify this, but it's true. You can look at this and understand it and ask me, but the point is that H inverse just looks almost like H, okay? Except that we replace omega by omega n inverse, omega n by omega n inverse. But once you know this, then it means that, okay, if we want to multiply any vector to H inverse, then it's just basically the same. You can do the same algorithm, like when you did for like in fast Fourier transform algorithm, except that you just replace omega n by omega n inverse. So just like use the same algorithm and replace everything, but replace the omega n by omega n inverse, and you're done. And then at the end, scale everything down by n, because H has this factor, like a scale everything down by n at the end. Okay. So that's why like the last step here, you can just use exactly the same algorithm. Just replace omega n by omega n inverse and you're done. Okay. So that basically completes the whole thing. You want to compute A times B. You get to this point first, like evaluate at omega to the I for all I, multiply pointwise, and use the same FFT algorithm, except that you replace omega n by omega n inverse and you're done. Okay. Question? Okay. So in the homework, you will see you need to think about you don't need to look into this complex number too much. There's no homework about that, it turns out. But I really wanted to try to tell you in full how fast Fourier transform is like, because it's such a really fundamental algorithm. But in the homework, you see okay, suppose that you can do fast Fourier transform fast. You can multiply polynomial fast. What else you can do with it? So there's gonna be a challenging homework question, and you can look it up. Okay. So now I'm gonna continue to the next topic. So which is the problem of selection. Okay. So imagine this, you have a tournament between many teams, right? And you want to find the champion. So you can it's like you have a bunch of number and you need to compare them, which one is the smallest. Okay. So if you have n teams, how many match do you need to find the best team? Can you tell me? Or if you have n numbers, how many comparison you need to do to find the minimum guy?
N.
n is enough, can you do better? If you have two team, how many comparison you need? One.
I wanna say it's like logarithmic.
Order of n is correct for sure, yeah. But I just want to say that actually n minus 1 is the correct answer. Yeah. Can you do better than n minus 1? Can you do it in n minus 2, for example? Who would think yes? Who would think no? Okay. Anyone have some reason why?
Well, if n is 2, you can't do n minus 2 because that would be 0.
Good. Yeah. If you have to, you need to do some comparison. In general, actually, if you have n teams or n numbers and you do n minus 2 comparison, there's going to be at least one guy that is not compared to any guy. And that guy could be a minimum guy, minimum one. So basically n minus 1 is just the best you can do. Okay. So what about if you want to find a second best team? Can you do it in 2n? Yes, 2n is enough. Just first find the minimum one and then do it again for like throw the best guy away and do again. So 2n is enough. But actually n plus log n is enough too. And the reason is this. Imagine that you do like this kind of, you pair up the team in this kind of tree, like a binary tree, right? So like suppose that this guy is the best guy. Oh, 1 second. So this guy is the best guy. So it keep winning, right? So what do you know? You know that like the second best guy must be the guy that lose to the best guy. The second best will keep winning until it compete with the best guy. Okay. But how many teams have been competing with the best guy?
Log n.
Log n, because that's the depth of the tree. So you just need to look among the log n many guys that lose to the best guy and find the best among that. So that's why it's just n plus log n. That's enough. So that's like a kind of nice observation. But the problem that we want to look at today is that, okay, what if it's the third one? What is the fourth one? What if it's just the kth guy that we want? Like you have n numbers, you want like the kth smallest element. How do we find it? Okay. So can you do it in n log n times? Anyone have idea how to do it in just n log n operation or comparisons? You have n numbers. You want to find the k smallest guy. Okay. Yeah.
You just sort it and then choose the K and then
Yeah.
log and sort it again.
Yeah. You sort it first. Sort everything first. That takes n log n operation, and then just look at the kth guy in your list. So that's good. So n log n is possible. Can we do better?
Couldn't you just like repeat the algorithm from above and then that would never be higher than O of n because you're just doing n plus like log n and then I guess you do another plus log n to find like the third worst guy.
So imagine that like so you said that okay, like we might just do like n and plus log n, and if you want to find the third, maybe plus another log n and keep adding a log n and so on. Okay. So that is like a good that is good if k is not too big, but suppose that k is like n over 2, then you might need to add log n over 2 times, so that's n log n. Okay. So what we're going to see today is that you can do it in order of n for any k, even when k is just n over 2, even when k is like n over 2, for example. If you want to find a median, you can still do it in ON. Okay. So again, this is a problem. You have set S, like n numbers. You want to find the k smallest guy. So the algorithm is like this. I'm not gonna tell you the whole algorithm yet. I'm just gonna tell you the template, and you guess how to complete the algorithm. Okay. So what we're gonna do is like to pick one element, pick an element E, just pick some, okay? And then compute the rank of E. The rank of E is just like, it's just the rank of E. And what you can do is just by like comparing E to every other element, that takes S minus 1 as comparison. After you compare E to everyone, then you are gonna get like that E is somewhere. This is the rank of E. That at the position rank of E, and this is like everything that is less than E and everything that is more than E. So you just compare E to everyone and obtain set S less than and S more than. So that kind of separate the set into two parts. So if it turns out that R, which is the rank of E, is exactly K, which is the thing that we want, then we are done. Just return E. What should we do otherwise if R is not K?
Just recurse on the subset.
Recurse on the subset. It's just the same problem with smaller size. You either recurse here or recurse here on S less than or S more than, right? So if like the rank that we want to find is less than R, rank of E here, just recurse on S less than, and you want to find the k smallest guy there. Otherwise, I will need to recurse on S more than, but the rank that I want to find is going to be k minus R there. Why is that?
Because it's not the complete set, so like, or it's hard to explain, but you don't want the, like, if E is like 5, you don't want the 5th smallest in the upper half.
Yeah.
Like the 15th if K is.
Right. Exactly. Like, for example, like the smallest guy here already has rank R plus 1 in the whole thing. Right. So if we want to find like a smallest guy here, like if we want to find the guy with rank R plus 1, we should like write down like 1 here. So like everything is shift. Like everyone here has some other numbers, many other numbers that is less than it. Okay. Okay, so that's the whole algorithm. Now let me ask you like, which element should we pick?
This is kind of like a partitioning quicksort where you just choose any number and then hope it's good.
Yeah, you can choose any number, but if you choose it like arbitrarily, then it could be that the algorithm is slow. It could be that like E could be at like the extreme, like the smallest guy, and every time you just reduce your problem size by 1.
Worst case.
And in the worst case, it's like n square.
Hopefully we pick the median.
Hopefully, yeah.
But there, I don't know how we can know for sure that we get the median though.
Yeah,
Determinist.
right.
I don't- that's right.
So it would be great if you can pick the middle guy, and so when you recurse, you get like a half and half size. Now we don't know anything. What should we do?
You need to calculate that it's constant meaning.
Yeah, maybe like pick a bunch of them and take a median among them. That's a good answer, and like it's how we plan to do actually. But it turns out that like there is just one simple trick to make this thing works, and it's just take the random guy, like not arbitrary one, but like a uniformly random one. Like just toss the coin and take the random one.
What's the difference? What's the difference?
Oh, by arbitrarily, then it means that the distribution of how you pick can be anything, but by uniform, it means that the chance that you pick everyone need to be the same. Yeah. So yeah, random and arbitrarily are not the same. Like when we say random in this class, we really mean something specific. That is, the distribution is really specific, it's uniform. For arbitrary, it's just we have no control. Yeah. Good. So that's the algorithm. Now, like we can try to analyze it. Okay, and this is a randomized algorithm. So the running time is the random variables, and so what we need to do is to compute it. Like the first step is to compute the expected value of the running time. So let this QKN be the expected number of comparisons made by this algorithm. And if you try to analyze this, it will lead you to like some complicated recurrence like this. Let me explain. Like, so this one is just when you compute the rank of E, right? And then and after that, like if the key is like if the key K is exactly the rank of E, then you are done. But otherwise, there are like n-1 other n-1 other event that can happen. That is like the rank of R can be like n-1 other place. Yeah. And so what you need to do is like just average over n-1 other events here, right? So this is the time that you need to spend when like the rank K is less than R. I mean K is less than the rank of E. Yeah, R. Yeah. Okay. So this is like you recurse on the left side here. And this is just the time that you need to spend when rank is more than K. So they just sum them up and average. So that's like what it means by expectation, right? Just average the time on all the events that can happen and multiply by the probability that it can happen. Okay, so that looks complicated and we don't plan to analyze this. Like it's just too complicated. So what we're gonna do instead is to actually simplify it. Like, okay, we're gonna simplify it so that it looks like something that more manageable to work with. How do we do with this? Like one idea is this. Try to let's say that I assume instead that I always recurse on the bigger side of my recursion. I analyze something different, which is the upper bound of what I need to analyze. But it's gonna simplify things. Why is that? Because if I always assume that I recurse on the bigger side of the problem, then now we can forget about k. Okay. It doesn't matter what k is. We're just gonna go to the bigger side anyway. So now this expression, this new process, just now is independent from k. But it's it's still upper bound of what we wanted to look at. So now the recursion looks like this: q of n independent from k, right? It's just like before, except that now we just assume that we go to the bigger side of the problem. Okay. There are the rank can be ranging from 1 to n. Just take the bigger ones from the 2 side. And this just simplify to this one. Because can just start from n over 2 to n instead of from 1 to n. And take the bigger one. And you get a factor of 2 here. And with this now it's looks simple enough, and we can analyze it now. Okay. So this is the recurrence that we have. And how do we do this? Well, obviously Master theorem is not enough, right? It's just this looks not applicable for Master theorem. And whatever recurrence you have, there is always an ultimate way to do this, to solve the recurrence. That way is just guess the answer and then prove that guess by induction. That's the ultimate way to prove recurrence. Okay, so let's guess that this is linear. It's order of n. So what I'm going to do is to say that, okay, for some constant c, q of n is at most cn. Okay. This is the same as saying that q of n is O of n, but you see that it's really important for me to specify the constant here. Okay. You see more precisely why later, but let me do it for now. I name the constant c here, and then let's prove this by induction. Where the base case c is big enough, just choose c to be big enough, bigger than q1 and some other number 8. Okay, so q1 is less than c trivially, so we are done. And for the inductive step, now it's just a sum calculation. Okay, it's nothing much. I just do the calculation. You have this. We have this before, and next step we use induction hypothesis. This guy is at most c times r minus 1, and next you need to do some calculation, and you see what you get. And now, because I choose my c to be bigger than 8, it's going to be the case that this thing is less than this. Doesn't matter, you don't need to follow this calculation, but you can see that by fixing c, specify c to be something bigger than 8, then this step works out. Okay. So if c is small, then the last step will not work. Okay. All right. So now you might see, okay, this is I hope that you don't need to follow calculation, but you see the pattern of the proof. Okay. Now let me give you one example why it's so important that I need to specify c, the constant in the big O. Okay. Let's see some wrong proof. Okay, this looks almost correct actually. I just said that q of n is order of O of n. I just write out this recurrence. Write out this is q of r minus 1. So write out O of r. So this sum looks like order of n squared. order of n squared over n, this looks like order of n. Everything looks good. The answer is correct. But there's something really wrong about this. Because if you just use this strategy, let's look at another really wrong example. Look at this recurrence. We know from master theorem that this solves to what? N squared. Okay. This is going to be n squared. But let's try to do something. Like, I assume, like, I want to prove by induction that actually this is order of n, which is wrong for sure. And how can I do this? Well, I can say that t of n is this thing. And by induction, t of n over 2 is just order of n over 2. This thing multiplied by 4 is order of n. So I somehow get that like a t of n is order of n. So something must be wrong. What was wrong? What was wrong is that the constant here and the constant here are different. So because when you hide this constant and they are different constant actually, then the proof goes wrong. So the point is that you must fix the constant inside the big O notation when you want to prove recurrence by induction. Okay. Question about this?
If the constant is like -1 or plus.
Say it again.
N over 2 -1, and this -1 is also constant. Can I just check it?
Usually the constant that you fix here is going to be positive. Yeah, not negative. What I mean is, like, when you write like t is order of n squared, like you assume that t of n is maybe like some constant c for maybe c which is like maybe larger than 100 or something. Like when you write order like O of something, this constant that you hide is a positive constant. Yeah. Okay. Anyway, that's like one thing that you need to do when you do like when you prove recurrence by induction. Be careful with a constant in the big O notation. Okay. Anyway, back to our quick select problem. So what we had before is like, okay, the random selection algorithm gives you order of n expected time. This is in expectation, but in worst case, how bad it can be? N squared, because you could, in like a very weird case, like you might keep getting the minimum, like when you random, when you sample, you keep getting the minimum guy. So the running time is like n squared. Okay. So now you can ask, like, is there a way, maybe the deterministic algorithm that always gives you linear time? So that's what we're gonna do today. Next. And it turns out that 50 years ago, Blum et al. Shows how to do this. Okay. And the idea is this. We kind of see before that, like when you choose an element E, it would be good if you can choose some element E such that they are kind of close to the middle. Because if it's close to the middle, when you recurse on both sides, then the size of the subproblem gets smaller by almost half. And that's good. Okay. So we're gonna do the same thing, but like the question is just then, how do we choose E in the middle? this kind of looks like a chicken and egg problem, right? Because if we know how to choose E in the middle, when then we would know how to pick the median already. But the question might be how to find the median fast. And here you said, okay, we want to find the median first. So that, but anyway, so here's an idea. So if if k is small, then we can do it fast. If k is let's say less than 5, then you can spend kn time, find the smallest guy first, find the second smallest guy, and find the third guy, and so that's just order of n. So when k is small, ignore this. It's fast. But in general, what we're gonna do is this. We have n numbers. Let's group them into a group of 5. Create a bunch of group of 5, like this, right? And for each group here, compute the median. Each of these is just a 5 number, so you can compute a median in constant time for each group. So you can compute these blue guys in order of n time. Okay. So that's a S prime. You can compute it in order of n. Okay. And now this set of medians from the group of 5, what I'm going to do is just to compute the median of this guy, of the blue guys, and get to the middle of this. How do we do this? You just say, okay, just recursively solve the problem, because this is just just smaller set, and we want to find the median. So just recursively look at this set S prime and find the middle guy. That's just recursion. Okay. Now I claim that there is something really good about this median of median. Okay. I claim that it's actually gonna be quite close to the median. It might not be the real median. The median will have rank 0.5s, but I claim that this guy will have rank kind of not too far, not too extreme. Okay. So its rank, if this is a thing, then there are 0.3 fraction here and 0.3 fraction here, and E can be only between, the rank of E is in this range. It's not on the extreme. So why is this the case? So the reason is this. So do you I'm just gonna draw an arrow like this. I point from the smaller guy to the bigger guy, right? And I also know that everyone here is smaller in this way. So it means what? It means that everyone in the blue box is bigger than E. Everyone in the red box is smaller than E. And I want to argue that the guy in the blue box is actually at least 0.3 fraction of the whole set. And similarly, the red one. Okay. So let me claim this. I claim that the size of this red box here, the size is at least 0.3s. Okay, why is that? So let's start by looking at this set. Okay. the purple set here is like a 3/5 fraction of the whole thing, because there are like 5 guys here, and I take like for every 5 points I take 3 points. So this is like a 5/3 fraction of the points, and the red set here is at least half of the purple set, right? So the red set is at least half of this, which is 0.3. So you get that the red set is at least like of size 0.3 fraction. The same argument goes for the blue guy. So it means what? The red set here, which is, it's going to be like there are 0.3 times S numbers that are smaller than E, which is the red guy is here. And there are like another 0.3 fraction of points that are larger than E. So the rank of E is between this, which is like what it means here. Yeah.
Was the number 5 chosen arbitrarily? Like why groups of 5?
Good. So you see that like if you do it for like a 7, like we want to do odd number so that the median is defined. For 7, for 9, for 11, you can do, everything will work actually. But like, what about 3, for example? It turns out that it's a research question. No one knows if it's a good algorithm yet. Yeah. Okay. Anyway, now you agree that the rank of E is kind of not on the extreme, it's close to the middle. So, okay. So this is what we get. Okay. Okay. And now we just continue in the same way. Now we know that E is some element that is kind of not median but works similar to median. It's like in the middle. So we just separate the set into 2 parts. The less than, S less than and S greater than, and do the same algorithm like before, recurse on both sides. So that's the algorithm. And I hope you are convinced that it's correct. What we need to do is just now to analyze the time. So what's the total time? Okay, we spend n comparison here, and here we spend like we recurse on the problem of size like a 0.2 fraction, because it's like 1/5 fraction of this, like just this set. So it's 0.2 fraction. And here we're gonna recurse on 0.7 fraction, because no matter what, when we recurse, we either throw this thing away or this thing away when we recurse on both sides. On either side, we throw like a 0.3 fraction away. So the size of recursion here is 0.7. So that's why this is like our recursion, like recurse on 0.2 fraction, 0.7 fraction, and order of n. Okay. So now just need to solve the recursion, the recurrence. And again, we can do this by induction. So this is not something that master theorem can solve for you, but like for me, when I see this myself, I can just what I do is like I just sum this thing up, and it's summed to like a 0.9n. And as long as the sum in this thing is like a strictly less than n by some constant factor, then I know already that this is gonna be linear. This is my rule of thumb, and it's true actually. But to do this like formally, you just need to prove by induction. And It's just the same kind of proof. Like the base case is good, and the inductive case you just write it down. This is by induction, and so it equals to this one. And then and I fix this thing to be C prime, right? And I want to prove that this is at most C. This C prime and C are not the same. Okay. And now I need to say that, like, I need to try to say that this thing is at most Cn. I want this. But to do this, to make this work, I just need to choose C to be bigger than 10C prime, which I can do. Like we can choose C to be, like, the choice of C here is our choice, right? We can choose C to be big enough so that the proof goes through. Just do that, and then it works. Okay. So indeed, we now get linear time algorithm that is deterministic. Okay. So that's it. Okay. And yeah, the question that you asked, like a Y5, what about 3? So if we just follow the same analysis, you're gonna get this kind of recurrent. This recurrent will give you n log n, which is as bad as sorting. However, it doesn't mean that it's a bad algorithm. It just means that this analysis gives you n log n. It's open actually whether like what's the truth, and you can, for example, just run the experiment and see what happened. For example, it's still open until now. And you can look at this paper if you are interested. Okay. All right. Questions? Okay. So I think let me like I was hoping to finish this thing. Let me talk quickly about this problem, like before we finish. Okay. The problem is like you have a graph and you want to find independent set, the big independent set. What is independent set? Is a set such that there is no edges inside it. For example, this is an independent set. This is also independent set because there is no edges connecting them. If you add this guy, then it's not, because now there are edges. So the problem is that you have a graph and you want to find independent set that is the maximum one, the biggest one. Okay. So it turns out that this problem is NP hard. And it means what? It means that you cannot expect polynomial time algorithm. Anyone have learned about NP hardness before? Okay, good. So yeah, so it's NP hard problem. But if you want to solve this in exponential time, can someone tell me some easy algorithm that can take like 2 to the n time?
You try each combination.
Yeah, there are like 2 to the n many subsets of vertices because there are n nodes. Just try all of them. So that's 2 to the n times polynomial in n. That's good. But we're gonna do better. Okay. So let's try like a one bad algorithm that will give 2 to the n, and then we improve it to be better than 2 to the n. So the idea is this. Suppose I fix one node v, right?
One contact.
Then there are just two choices about v. Either it's inside a set or it's outside. So let's try, like suppose that, okay, we have two choices about v. Suppose that we guess that it's not in the optimal solution. So just exclude it from the graph. And if this guess is correct, then we can just recurse on the rest of the graph without v. And if this guess is correct, then you will get the correct answer. this guess might be wrong. So it could be that actually V is in your solution. So we can guess again that V is in the solution. But now something better actually happened. If V is in the solution, when we want to recurse, we don't just need to remove V. We can just also remove neighbor of V. Why is that? Okay.
Well, because if they were in the set, then it wouldn't be an independent set.
Yeah, like if V is in the independent set, then you know for sure that neighbor of V will not be in your solution anyway. So you can just exclude all of the neighbor of V. Okay? So that's the idea. And just basically this is the algorithm. Try the case when when V is not in the set, and try another case when V is in your solution. This is a case when you include V into your solution and now recurse on the graph where you throw everything away, including the neighbor of V. And then just return the best of the two guesses. And that's it. That's the algorithm. But the recursion looks like this. In either case, you know that the graph size is reduced by at least 1, and you try 2 guesses. And you spend maybe linear or polynomial time outside. And when you solve the recursion, you can do it by unfolding. You can unfold this n times, you get to the end. Not great. But okay, this analysis seems loose actually, because you see that when you remove, in the case when you remove the neighbor of V, you expect to remove more than 1 node, right? Because that should be the neighbor of V. So in this case, you expect that there should be strictly less than n minus 1. Okay. However, it could be that even when you want to remove neighbor of V, this graph still have n minus 1 vertices, because it can be that a V has no neighbor. Degree of V is 0. But if you have a graph and 1 node has no neighbor at all, what should you do about it?
Include it?
Just include it. If there is some isolated node, it should always be in the independent set, in the maximum independent set. So there is not, this case when there is a node with degree 0, it's an easy case. There's no choice, you just include it, right? So that's the point. If degree of V is 0, must be in every maximum independent set anyway. We need to include it. So it means that if degree V is 0, there's no branching, there's no guess. Just include it. And if degree of V is more than 0, then just use the same algorithm like before, try both, right? But in this case, we get something nice. The recursion is actually now better. Why? Okay. So the recursion now looks like this. If with degree V is 0, no branching, just include it and recurse on the smaller graph. Otherwise, you look at the 2 cases. This is the case when you exclude V, but this case when you remove V together with its neighbor, there are less than n-1 nodes now. Okay, so that's the better recursion. So this case dominates everything, so the recursion looks like this. Okay, so it's actually a bit better, but now I claim that this recursion can be solved to something better than 2 to the n.